And I'm at home now, so I'm going to try out some new styles of video taping and we'll see what works out. But let's continue with 7.5, which is calorimetry problems with phase change. Okay, so first of all, we looked in the last lecture about how when heat is added to a substance, the first thing that can happen is that it can change the temperature. We also know the second thing that can happen is that it can undergo a change of phase. So we have three phases: solid, liquid, and gas. In a solid, the molecules are tightly packed together and they can vibrate and move around, but they can't move freely. The next, more energetic state is a liquid, where the molecules are weakly held together by bonds, but they are free to move. And our most energetic state is a gas, and in a gas, the molecules are free to move. The intermolecular forces are much less significant in that case, and that's so they have the most energy as they move in a gas. Okay, so transitions between these three states are called phase transitions or phase changes. And generally, phase changes in an isolated system will occur at a constant temperature. So let's look at this graph, which shows what happens when we take ice from the freezer at minus 20 degrees and then we add heat to that ice. So we have temperature on the y-axis and then heat added on the x-axis here. So the first thing that happens at negative 20 is that any heat added goes into warming up that ice. So that ice will increase temperature until it gets to its melting point at 0 degrees. And at 0 degrees, that's when it starts to melt. So now at 0 degrees, if it's isolated, only heat is coming in that we're adding in this linear way, is that at that point, all of that heat will go into melting the ice. And it will remain at 0 degrees until all of the ice has melted. So our phase change is happening in this horizontal line on the temperature versus heat diagram. The width of the phase change line here represents the amount of energy added. Okay, so that's the energy to convert all of it to ice. Now when all of the ice is melted, any heat that's added will go back into heating the temperature of what is now liquid. So now the liquid will increase its temperature until it gets to 100 degrees, which is the boiling point. And I suggest remembering 0 degrees and 100 degrees. We probably already know them and they come up a lot in this section for water. Okay, so now that liquid water, when it gets to 100 degrees, it will then undergo a phase change where it's evaporating. In that evaporation, this is a longer width than this melting phase because it requires more energy, but it will remain at 100 degrees until all of it turns into steam, and only then will any more heat added go into heating the steam further, and this, in this case, up to 120 degrees. So some notes on this: we know that the width of the line represents the heat added. Also, the slope of this line represents the specific heat, but it's actually inversely proportional to the specific heat. So these phase change terms are mc delta T, that's the amount of heat added. And this will have a shallower slope, more shallow slope, if C is larger. If we put delta T equals Q over mc, C is in the inverse. Q is our x variable and delta T is in the y. So a higher specific heat means more energy required, and thus that would be a more shallow line and covering a greater width. Okay, one more thing I should mention is that these boiling point and the melting point, they do depend on thermodynamic conditions for the substance. For example, pressure and purity. So an example of this is, you might have heard that water will boil faster at a higher altitude, and that's where the pressure is lower. And then also we have the substance's purity. That's why we would use salt or antifreeze to prevent ice to lower the freezing point of the water. Okay, also we know that energy is added to move to a more energetic state. Energy is also released if it's going the other way. If we were to start with a gas and condense into a liquid, that would release energy. And same thing for starting with a liquid and condensing into a solid, that would release energy instead of requiring it. All right, so let's look at how to solve problems with the phase change. Okay, so when we write out our heat transfer equation, when we have substances in a system for a calorimetry problem, we still want to have the sum of all our Q values for the system adds to 0 if we're talking about isolated systems. There's no heat transferred into or out of the system. It's not quite what happened in that last example. We were adding energy, so this would be a thermal equilibrium problem. So when we have a heat change, we know that's Q equals mc delta T. For a phase change, the energy term is called the latent heat. And the latent heat Q is plus or minus mL. So in this expression, we need to decide two things. First of all, L can be either LF, which is the latent heat of fusion, or LV, which is the latent heat of vaporization. Both of these constants are measured in joules per kilogram, and they give the amount of energy required to convert 1 kilogram of a specific substance into the other phase, into the next phase. So if we're talking about latent heat of fusion, this is the energy required to convert 1 kilogram of a substance from either a solid to a liquid or a liquid to a solid. It would be the energy released from a liquid to a solid. So if you're using a solid, you use the latent heat of fusion. If it involves a gas, we're going to use the latent heat of vaporization. The latent heat of vaporization gives the energy required to convert 1 kilogram of a substance from a liquid to a gas or a gas to a liquid. And it would be released in that case. So these are specific to the substance. So you can look up a latent heat of fusion for water or for any other substance that you need. You can find those values. Usually in a chart, and if you look in my lecture slides, there is a chart there as well, or it will be given with the problem. Okay, the second thing we have to decide is whether to use positive or negative, and we do have to assign this here, unlike with the temperature change term where it comes from the temperature change. So positive is going to be if this energy is required for the phase change to occur, and the negative sign we'll choose if this is energy released. So if this is going to be energy that's released as the substance changes from a more energetic to a less energetic stage. All right, so let's do some examples here. I'll just pause for a second to set up the first example. All right, so our first question is that water has the following latent heat values: latent heat of fusion of 333 kilojoules per kilogram, and a latent heat of vaporization of 2,260 kilojoules per kilogram. How much energy is required to melt 200 grams of ice? What about to vaporize 200 grams of water? And we can assume they're already at the melting and the boiling point. Okay, so if you have a look at my board, I've written the values here and set this up. Q equals plus or minus mL. So first we are melting 200 grams of ice. Now this requires energy to melt ice, so we want positive, and then we'll have M, put in kilograms to match our units here, and then we can leave this in kilojoules. We'll choose LF because this transition involves a solid, and then if we multiply through, we get our answer in kilojoules as well. It's 66.6 kilojoules. Okay, and then to vaporize 200 grams of water, this time we want to use the latent heat of vaporization, and this also requires energy, so it's positive. 0.2 kilograms times 2,260 kilojoules per kilogram. Notice it takes more energy to vaporize the water than to melt it, and we get 452 kilojoules. Okay, moving on to the next example. Suppose you want to raise the temperature of 100 grams of ice from -20 degrees Celsius to generate steam at 120 degrees Celsius. How much energy is required? Okay, let's go through all of the steps and I'll make do with my small board and we'll write one long equation here to calculate the total energy. This isn't an isolated system. We're adding in energy and we just want to know the total energy needed. All right, so our ice is starting at negative 20 degrees Celsius, just like the diagram I drew. You can think about that kind of heat, temperature versus heat diagram, and then every time there's a straight line, we need a different Q value for that term, if that helps. Or just track the substance all the way through so that you can find the total heat required. Okay, so first when we have our ice at minus 20, we're first going to want Q to warm the ice. We'll warm that ice to 0 degrees Celsius. Okay, now it's at the melting point, we can melt the ice. After all the ice is melted, then we can heat that melted ice, which is now water. So let's warm that water or that melted ice. And then it will warm up until it gets to 100 degrees. So to 100 degrees using some long subscripts here. And when it's at that boiling point, then we'll have the vaporization. So plus Q, vaporize the water. And then lastly, we can finally heat that vapor or the steam up to the final temperature of 120 degrees. So let's go through and make sure that we get all the terms correct here. So first I'm going to warm ice. This is going to be the mass. All the mass will be the same throughout, so I'll just leave that as M. Latent heat of fusion for going, oh, that's our next term. I'm just warming it first, so C ice. And then my temperature here, I'll put in the temperature change just to avoid many temperature subscripts. So it's going to 0 degrees from negative 20. Okay, so that's our first term. And now we want to melt ice. So plus the mass of ice, latent heat of fusion of ice. So this term is positive because it requires energy. Again, we don't assign it to the temperature terms, that comes out of delta T, but we do need to assign it to our latent heat terms. Okay, now warming the water plus the mass, they're all just M. C water, this is going to 100 degrees from 0. Now vaporizing the water, again, requires energy, still going up on that energy scale, and this time we need the latent heat of vaporization. So plus MLV, and then finally heating the steam, CS for C steam, and that's going to 120 degrees from 100. And that's it. You can calculate each of these terms in steps if you like. I did it that way in my lecture notes. But here we can do it all in one line, which works too, and just plug in all the numbers at once. Just to simplify, since the mass is always the same, I'm going to put that out front. So 0.1 kilograms for the mass. And then I'll have C ice, which is 2100 joules per kilogram, degrees Celsius, times, this works out to 20 degrees, plus the latent heat of fusion, 333,000 joules, plus seawater, 4,186 joules per kilogram, degrees Celsius, times 100 degrees, plus the latent heat of vaporization, 2,260,000 joules, and then plus our last term here, C for steam, which is 2010 joules per kilogram, degrees Celsius, times 20 degrees from this bracket here. You can pause that if you want, if I was going a little bit quickly with that equation, or again, see the notes. And then when I calculate that, I get 3.09 times 10 to the 5 joules, which is the total energy required to take this ice at negative 20 degrees all the way to steam at 120 degrees. Okay, so more often we will be instead doing calorimetry problems where we have multiple substances, we're putting them into an isolated system and allowing them to come to an equilibrium temperature. What I said in the last section still applies. So these substances will exchange energy until they all arrive at thermal equilibrium and are all at the same temperature. And now it means that sometimes phase changes will have to occur in order for that to be possible. So we want to write the sum of all Q equals 0, and we're going to have a term for each substance's temperature changes and each substance's phase changes. So I'd suggest starting with one substance and tracking it through the process. So what happens first and where does it end up? And put a Q value for each term. Also, make sure to have one for a temperature change for each substance. Notice in the last example, we couldn't do one temperature change for the ice from -20 all the way to 120 because the C values are different depending on its phase. So C, the specific heat is specific to the phase of the substance. So we do need to do those as separate terms. But okay, let's look at the first example. Okay, so you have taken ice from the freezer at -20 degrees Celsius. How much ice must you add to 500 grams of diet soda at 30 degrees to cool it to 5 degrees? All right, so let's track this through. 5 degrees is the final temperature of the soda, which means everything in the system has to end up at 5 degrees. And if that ice is now at 5 degrees, it has to be water. So we know that the ice is going to melt. But it can't melt yet. So if we look at the ice, it first has to warm up to 0 degrees, and then we'll need a term for melting the ice, followed by a term to warm up the ice, and a term to cool the soda. So once the ice is warm to 5 degrees, we also need that last term to cool the soda to 5 degrees. This is the most important part, so make sure to go carefully through each substance and make sure you have a Q value for each one. All right, so let's keep going. We have M for the ice, C ice. I think putting in the temperatures here saves a bit of confusion with subscripts, so I will continue to do that. So our ice was going from to 0 degrees from -20 again, plus the mass of the ice times the latent heat of fusion. Again, checking that this is a process that requires energy, and it is, so that's positive. And we're using the latent heat of fusion. Okay, and then warming up the ice. It's still the mass of ice, but now we need seawater, since at that point the ice has melted and it's water. And that's going to 5 degrees from 0. And then I have this last term, which I'll have to write down here, plus the mass of the soda, or pop, and then that is seawater. We can assume that it's very similar to water and use that constant. And all of these constants are in the data sheet if you need to find them there. Okay, so then this is going to be going from its original temperature of 30 down to 5, so we have 5 degrees minus 30 equals 0. Okay, and we're solving for our unknown, which is the mass of ice here. So I'm going to pull out the mass of ice and everything that's in it. So I have sea ice. This is 20 degrees plus the latent heat of fusion plus seawater times 5 degrees. And I'll move everything we don't need to the other side, which is this term. Mass of soda, this is for soda, seawater times 25 degrees. This was negative, it was negative 25 degrees, so I'm moving it to the other side and now it becomes positive 25 degrees. Okay, so I'll divide by this whole bracket. I'll plug in the numbers at the same time just because I'm a bit out of space, but again, for more detailed calculations, you can check my notes. So I'm going to take this divided by this whole bracket. So that's going to be 0.5 kilograms for the soda, 4,186 joules per kilogram degrees Celsius for the water times 25 degrees, over C for ice, 2,100 joules per kilogram degrees Celsius times 20 degrees, plus 333 times 10 to the 3 joules per kilogram for water. And then, over here I have plus 4,186 joules per kilogram degrees Celsius times 5 degrees. Okay, and then you can calculate all of that, which will give us a positive solution of 0.132 kilograms, or 132 grams. Okay, let me know if you have any questions, and for now I'll go on to the next example. Okay, for the next example, suppose the diet soda and ice water combination from the above question is at 5 degrees. You add in another 20 degrees of ice from the freezer, also at minus 20 degrees. Does all of the ice melt? If so, what is the final temperature of the mixture? If not, how much ice is left? So we don't always know whether or not a phase change will occur. We can use the energy available versus the energy required to determine if the phase change will happen. So our method is that we're first going to determine if there is enough energy to melt the ice. And if there is, it will happen because the energy from cooling the soda needs to go somewhere. Okay, so let's look at how much energy needed, Q required, to melt the ice. So first, our ice that we're taking is again at minus 20, and we need to warm it up. So let's warm the ice to 0 degrees. And then melt the ice. So this will be the mass of ice, C ice, 0 minus negative 20, plus the mass of ice times the latent heat of fusion, just like the last question. And we can find this number here, so 0.020 kilograms times 2,100 joules per kilogram degrees Celsius times positive 20 plus 0.020 kilograms times the latent heat of fusion, 333 times 10 to the 3 joules per kilogram. Okay, so this requires 7,500 joules in order to melt the ice. Let's keep that number, but now we'll check, I'll erase this, and we can check how much energy is available if the soda were to then cool to 0 degrees. So if only part of the ice melted, we know that the soda would end up at 0 degrees because the ice would have to be at 0 degrees and everything has to be at the same temperature. So our Q available by cooling the soda would be Q to cool the soda to 0 degrees. So that's the mass of the soda. By the way, the mass of the soda now is 0.632 kilograms because we've added in that melted ice from the last question. So now there's extra liquid or water in that soda mixture. MS, seawater, going from 5 to 0 degrees. So 0 degrees minus 5. 0.632 kilograms, 4,186 joules per kilogram degrees Celsius times minus 5. And in this case, I get negative 13,227 joules. This is the energy available to be released, that's why it's negative, by cooling that soda. Notice that's much greater than the energy required to melt the ice. So this tells us that yes, all of the ice melts. Again, that's because our energy available to be released is greater than the energy required, so it does melt. Now, if it didn't melt, if we found that this was smaller, at this point what we would do instead is set up our calorimetry equation, and we know the final temperature was 0, and we would solve for the mass of ice that melted. So the mass of ice that melted would be our unknown, maybe mx. We'd have to warm all the ice to 0 degrees, but then solve for the mass that melts. But in this case, it does all melt. So now let's find the final temperature of the mixture. Okay, so if we set up our calorimetry equation or thermal equilibrium equation, I have Q, again, warming the ice to 0 degrees, and then melting the ice, warming the melted ice. So we saw that it was about 13,000 energy available and only 7,500 needed to melt the ice. That extra energy will then go into warming the ice up past 0 degrees. So we want that term. We don't know what the final temperature is, but we're going to find it. Plus Q to cool the soda. Now we calculated Q cool the soda to 0 degrees, but because there was extra energy, it will actually warm up that melted ice and the final mixture will be above. So we can't use Q soda from the previous, what I had written here, because it's actually going to now cool to a higher temperature. So it will cool less since all of that energy wasn't required, but we can use all of this. We know the energy to warm the ice to 0 and to melt the ice. That was 7,500 joules. So we don't have to recalculate that. So we have 7,500 joules plus the mass of water, seawater. And then this temperature is going to be the final temperature T minus 0 degrees, where this melted ice started, plus the mass of the soda, seawater. This is going to the final temperature from 5 degrees. Okay, so T minus 5 and all of that equals 0. So I want to solve for this unknown temperature here. So I have, see how I can rearrange this quickly. I'll expand first. M water, C water, T minus 0, that term will go to 0, so I won't write it, plus the mass of steam, C water, T minus the mass of, I keep saying steam, soda, seawater times 5 degrees Celsius equals 0. And now I'm going to keep those on the left and rearrange, so I'll get T equals mass of soda, seawater, times 5 degrees Celsius minus 7,500 joules over M water, seawater, plus the mass of soda, seawater. All right, I'll erase and then I will plug all those numbers in a second. So I'll just erase this top, but you can always pause it to see. All right, so taking that up a bit to plug in the numbers, that's 0.632 kilograms, 4,186 joules per kilogram degree Celsius times 5 degrees minus 7,500 joules over 4,186 joules per kilogram degree Celsius. That term is here both, CW here, so I'll add the masses here, 0.020 kilograms for the ice. So this was actually ice in here. Yeah, soda and then water, it was ice or melted water. 0.020 kilograms plus 0.632 kilograms to get the total. And that gives me 2.1 degrees Celsius. So it makes sense it ends up somewhere between 0 and 5 degrees, and that extra energy went into warming the ice. Okay, just one more example in this section. Okay, so a 70-gram bullet traveling at 250 meters per second penetrates a block of ice at 0 degrees Celsius and comes to rest within the ice. If the temperature of the bullet doesn't change significantly, how much of the ice melts? This is an interesting question where we have this bullet initially moving at 250 meters per second. It will collide with the ice, and we can assume that all of that energy goes into melting the ice. So we have a transfer of kinetic energy of the bullet into the thermal energy of melting the ice. So we have delta K E plus Q equals 0. We don't write delta Q, but Q does mean a change in energy or a transfer of energy. So KE final, it's a conservation of energy question, minus KE initial plus Q equals 0. And the bullet ends up at rest, so KE final is 0. So we'll have negative 1/2 mv squared plus, because it requires energy to melt that ice, the mass of ice that melts times the latent heat of fusion of water, which equals 0. This is the mass of the bullet. Maybe I'll put MB to indicate that it's the bullet. So then MI will equal 1/2 mass of the bullet V squared over the latent heat of fusion of water. So 1/2 0.070 kilograms, 250 meters per second squared, all over 333,000 joules per kilogram. Okay, and that final mass is 0.00656 kilograms. Which is, I'll just put it here, 6.56 grams for that final result of the amount of ice that melts. It's not very much, and the bullet was moving at 250 meters per second. So it's a good example of how it takes a lot of energy to melt ice. But okay, that's all for this section. You can email me if you have any questions.